Hello students, welcome to the online class for Automobile Component Design Lab. The subject code is ACTL. This particular design lab is present in your 5th semester diploma syllabus for Department of Automobile Engineering. Let me first introduce myself. My name is Tanmoy Kundu, Assistant Professor, Department of Automobile Engineering, Dr. Sudhir Chandra Sood, Degree Engineering College, Kolkata. Today we have the practical activity number 3A, topic design of Cotter joint part B. So as you know, in the previous lecture I have discussed the part A of the Cotter joint design, where I have discussed broadly the definition of the Cotter joint, the introductory part of the Cotter joint, the several components, and also the theoretical aspect of the failure of the different components in the Cotter joint, and thereby considering the failure of those components, we have derived some mathematical equations to reach the expression for obtaining the different dimensions of the Cotter joint. Okay, so as you know, we have in our syllabus mostly the socket and spigot type Cotter joint. So coming back to the socket and spigot Cotter joint, so today we'll discuss a numerical part on considering the different failure aspect to obtain the design dimensions. So let us start. So as you know that socket and spigot Cotter joint, this is the socket and spigot Cotter joint. So in socket and spigot Cotter joint, one end of the rods, so say this is the rod A, so it's provided with a socket type of end. Okay, so this is the socket type of end. So one rod A is entered into this socket, and the other end of the rod like B, so B is the another end that is inserted into the socket. The end of the rod which goes into the socket is called the spigot. So this is the spigot part. So spigot part is basically the blue colored hatch line is the spigot part, and the red colored hatch line is the socket part. Now there is a rectangular hole that is made in the socket and spigot. So the cotter is then tightly put through those rectangular hole in order to make the temporary connection between these two rods. But one thing we have to remember, here the load applied, that is the P may be a tensile type of load or maybe a compressive type of load. So here the load must be acting axially, but it can change the direction. Hence the Cotter joint must be designed to carry both the tensile and the compressive load. Now the compressive load is mostly taken care of by the collar of the spigot. So this is the collar of the spigot part. Okay, this is the collar of the spigot part, this one. Now with respect to this design aspect, one thing we have to remember, that the central axis of these two rods must be in the same axis, coaxial. Okay, so only then we can design the Cotter joint. So this is one view, and if you view this Cotter joint from this angle, so we can see some concentric circles, and there is a rectangular hole, rectangular slot through which the cotter is inserted. Okay, now coming back to the dimensions. So first of all, P. So P is the load carried by the rods. Small d, that is the diameter of the rods. D1, here we see D1 is the outside diameter of the socket. D2 is nothing but it is the inside diameter of the socket, and within this particular diameter the spigot is entered. So the diameter of the spigot is equal to the inside diameter of the socket, and that is denoted by D2. D3 is the outside diameter of the spigot collar. So this one is the D3. T1 is the thickness of the spigot collar. This is T1. This is T1. This is collar thickness. Okay, spigot collar thickness. D4 is the diameter of the socket collar. So this is D4. This one is the socket. So the socket collar. This is D4. The entire dimension. So this is D4. This is diameter of the socket collar. C is the thickness of the socket collar. This is C. Okay. B is the mean width of the cotter. This one is the B. This is mean width of the cotter. Why mean width? Because we see that cotter is basically a tapered part. So upper part is having the higher width and the lower part is having the minimum width. So obviously we have to consider the mean width value or the average width value, that is considered as B. T is the thickness of the cotter. This is T. L is the length of the cotter. This is L. A, that is the distance from the end of the slot to the end of the rod. This one is the A. Sigma T is the permissible tensile stress for the rod material. Tau is the permissible shear stress for the cotter material, and sigma C is the permissible crushing stress for the cotter material. So we have to consider these three important stress points. Okay, so tensile stress, compressive stress, and as well as the shear stress. Now the dimensions for a cotter and spigot joint may be obtained by considering the various modes of failure, so as discussed below. Now, so considering the different failure modes of the different components used in cotter joint, so we basically obtain some dimensions, all the dimensions, that is the L, like T, then D, D1, D2, T1, D2, everything is all the available dimensions we get by considering the different modes of failure of the different components used in the cotter joint. So considering that fact, so let us solve one numerical, so that will give us much more idea. So design and draw a cotter joint to support a load varying from 30 kilonewton in the compression to 30 kilonewton in tension. The material used in carbon steel, for which the following allowable stresses may be used. The load is applied statically. So first of all, here it is given the we have to draw and also we have to design and also draw a cotter joint. So that will carry the load like 30 kilonewton. It may be tension or it may be a compression type. So the material used here, the carbon steel. Okay, and for the carbon steel material, the allowable stress values are given, like tensile stress equal to compressive stress, that is given 50 MPa megapascal, that is 50 Newton per millimeter square. Shear stress is given 35 MPa and crushing stress is given 90 MPa. So these are the all information given. So based on that, we have to design the cotter joint. We have to obtain the different dimensions of the cotter joint considering the failure modes of different components, like failures of cotter, failures of the cotter, failures of the rod, failure of the socket, failure of the spigot, all those aspects we have to consider. Then we have to get, although we have already figured out the mathematical expressions in the previous lecture, so considering those lectures, considering those important mathematical formulas, so we'll just use those formulas to solve the values and to get the values and design, and then finally we'll draw that. Okay, so here P is given. So given data, capital P is 30 kilonewton, that is 30 into 10 cube Newton. Sigma T is given 50 MPa, so 50 Newton per millimeter square. Tau is given 35 MPa, that is 35 Newton per millimeter square. Sigma C, that is the crushing stress, that is given 90 MPa, so 90 Newton per millimeter square. So let us start with the diameter of the rod. So first of all, we have to obtain the diameter of the rod. So let's, as we know that D is the diameter of the rod. So considering the failure of the rod in tension, we know that P, that is the applied load. Okay, so P is equal to pi by 4 d square into sigma T. Okay, so sigma T, here the sigma T value, if you put the sigma T value, that is 50, so we get the value of the diameter of the rod as 28 millimeter. Okay. Next, diameter of the spigot and the thickness of the cotter. Okay. So diameter of the spigot, let us consider the diameter of the spigot, that is the inside diameter of the socket, which is d2, and t is the thickness of the cotter. So cotter thickness, as you know, t equal to d2 by 4. So if you get the value of d2 and if you divide the d2 with the 4, so we obtain the cotter thickness. So considering the failure of spigot in tension across the weakest section, so the mathematical formula is P equal to pi by 4 d2 square minus of d2 into t. So this is the overall area and this is the net area where this sigma t will be acting. So pi by 4 d2 square minus of d2 into sigma t. Okay. So put the value of t equal to d2 by 4. So we have obtained the value of d2 as 34 millimeter. So the t2 will be 34 by 4, that means 8.5 millimeter. So cotter thickness is 8.5 millimeter and the spigot diameter is 34 millimeter. Okay, so cotter thickness 8.5 and the spigot diameter is 34 millimeter. Okay. Let us now check the induced crushing stress. So what is the value of crushing stress? So let us check. So we know that P equal to d2 into t into sigma c. Okay, d2 into t. d2 means it is the spigot diameter and t means it is basically the thickness of the cotter. Okay, so d2 into t, so it is a rectangular section when it is multiplied by the sigma c. So ultimately sigma c is coming 103.8 Newton per millimeter square. Okay, this is the induced crushing stress. Now since the value of sigma c is more than the given value of sigma c, that is 19 Newton per millimeter square, so the matter is that, so allowable sigma c is given 90 Newton per millimeter square, but the induced shear stress, induced crushing stress that is generated due to the application of the external force P, so this induced crushing stress is more than the allowable crushing stress. So therefore the dimensions of d2 equal to 34 and t equal to 8.5 are not safe. That means we have to manipulate the data, we have to change the data accordingly. So we cannot consider this data, otherwise the material will be failed by means of the crushing. Now let us find the values of d2 and t by substituting the values of sigma c equal to 90 Newton per millimeter square. Okay, so sigma c will put here the 90 Newton per millimeter square in the above expression, that is 30 into 10 cube in this expression, 30 into 10 cube into d2 into t into 90. Okay, 30 into 10 cube into d2 into t into 90. Okay, so here it is coming, as you know, so it is in place of t will write d2 by 4, so it is coming like d2 equal to 40 millimeter, so t equal to 10 millimeter. So previously d2 was 34 millimeter, so considering the safety aspect, so the dimensions have been really increased. So diameter of the spigot has been increased from 34 to 40, and also thickness of the cotter is increased from 8.5 to 10 millimeter. Okay, so now the design is absolutely safe, so we can go ahead with those dimensions. Next come to the outside diameter of the socket, so that is the d1. Let d1 is the outside diameter of the socket. So considering the failure of the socket in tension across the slot, so as you know that P equal to, so pi by 4 d1 square minus d2 square minus of d1 minus d2 into t. This is the as you know, in the previous class I have already told you that this is the diameter, this is the area of the slot. Okay, so that part is been deducted from this overall part, and it is multiplied by sigma t. Okay, so d2 we have already got 40, so put that d2 equal to 40. Finally this is the quadratic equation we have obtained, so d1 is coming like 50 millimeter. Okay, d1 is coming the 50 millimeter. Now come to the width of the cotter, that is b. So as you know, the considering the failure of the cotter in shear, since the cotter is double shear, therefore the load P equal to double shear, that is multiplied by 2, so 2 into B into T into tau. So 2 into B into T. T means Cotter thickness we have already calculated 10. So tau is given 35. So it is coming B equal to 43 millimeter. Okay. Now the diameter of the socket collar, that is D4. So considering the failure of the socket collar and Cotter in crushing, so we know that P equal to D4 minus D2 into T into sigma C. So as we have already gone through this thing in the previous class. So put D2 equal to 40 millimeter and T equal to 10 millimeter. So it is coming D4 equal to coming 75 millimeter. Okay. Now thickness of the socket collar. So C is the thickness of the socket collar. So considering the failure of the socket end in shearing, since the socket end is double shear, so therefore P will be equal to 2 times multiplied because in double shear. So area is D4 minus D1 into C and the stress is tau. So putting all the values of D1 and D4, so we have finally obtained that the C is equal to it is coming like 12 millimeter. Okay. Now distance from the end of the slot to the end of the rod, so that is the value of A. So how can you obtain? So considering the failure of the rod in shear, since the rod is in double shear, so therefore load P equal to 2 into A into D2. A into D2 means it is the area multiplied by the tau. So it is coming ultimately A equal to 11 millimeter. Okay. Now diameter of the spigot collar. So spigot collar diameter, as you know, it is denoted by D3. So considering the failure of the spigot collar in crushing, so we note P equal to, so P equal to 30 into 10 cube, that is equal to pi by 4 D3 square minus D2 square. This is the overall area on which the sigma C is acting, so multiplied by sigma C. So putting the value of D3 and putting the value of D2, we have obtained the D3 value as 45 millimeter. Next come to the thickness of the spigot collar. So let, as you know, that spigot collar thickness is selected as T1. So considering the failure of the spigot collar in shearing, so we know that P equal to, here the spigot collar fails in single shear, not the double shear, so we have to remember that. Okay. So P, that is 30 into 10 cube, equal to area multiplied by shear stress. So area means it is pi D2 into T1, so multiplied by tau. So putting the value of D2 as 40 and tau equal to 35, so the T1 value is coming like 6.8 millimeter. So nearest data is 8 millimeter, nearest standard data 8 millimeter. So we can consider that the thickness of the spigot collar is 8 millimeter. Now point number 10. So the length of the Cotter, that is L. So L, we know the formula L equal to 4D. D is the diameter of the rod, so it is coming like 28 millimeter. So when it is multiplied by 4, so the length of the Cotter is coming 112 millimeter. Okay. Now the final dimension of E. Let us go to the drawing again. This is E. Okay. So how much is the value of the E? So E value is coming, as you know, the formula E equal to 1.2 into D. So rod diameter will be multiplied with 1.2, so it is coming 1.2 into 28, so 33.6 millimeter. So we have selected 34 millimeter, like, so dimensions of E is coming like 34 millimeter. Okay. So this is the design part. So as per the dimensions obtained, so we have to draw the Cotter joint accordingly by means of the AutoCAD and also by means of the CATIA. So both these two softwares will be used to draw this particular Cotter joint. Okay. So in order to draw this joint, we have already calculated all the dimensions as per the design calculations. So use those dimensions and finally draw the Cotter joint. Okay. Now this is the reference textbook. So R.S. Khurmi, textbook of machine design by R.S. Khurmi and J.P. Gupta. So this book I have used for as a reference purpose. for this particular design calculations. So okay, so I believe that this particular topic is very much understandable to you all. So you are all advised to go through the study material and also practice the calculation aspects. Okay, so design calculation is a little bit that is somehow it's complicated. That means it basically includes the different types of stress and different types of dimensions are there. So which dimensions will be used, so that thing we have to apply some kind of logic and some kind of understanding to go through the study material properly. Okay, so I'd like to end my session right at this moment. So in the next day I shall start with a design procedure for a different component. So thank you very much.